The primary function of an antenna is focusing when it is working in transmitting mode, and it is collection when the antenna is functioning in the receiving mode. Antenna is supposed to focus all its input power towards the receiving antenna, and the receiving antenna is supposed to collect all the signal power that is available in front of it and hand it over to the receiver equipment. Now, a few points regarding the parameters which are used to indicate the capability of an antenna to focus its input towards the receiver, and also capability of the antenna to collect the signal that is coming from the transmitting antenna and hand it over to receiver equipment. The parameter that indicates focusing capability of the antenna is directivity or gain. By definition, directivity is maximum radiation intensity to average radiation intensity ratio. But average radiation intensity is total radiated power to 4 pi ratio. Hence, directivity can be found as 4 pi times maximum radiation intensity to total radiated power ratio. From this relation, one can see directivity is more when maximum radiation intensity is large. Maximum radiation intensity becomes large only when the antenna is able to focus more and more. Hence, we can easily understand that directivity gives a measure of focusing ability, focusing capability of an antenna. In the denominator, if we use total input power instead of total radiated power, then directivity becomes gain. Gain also can be considered as a parameter capable of indicating the focusing ability of a transmitting antenna. Now, a few points on a parameter which indicates the collecting ability of the antenna. Signal power attracting ability of an antenna while it is acting in receiving mode. It is effective aperture. Aperture means an opening through which incoming wave enters into the antenna, receiving antenna. By definition, effective aperture is power available at the antenna terminals over power density in front of the antenna. Power available means maximum power that can be drawn from the antenna. Effective aperture naturally is more when power available at the antenna terminals is large, and available power at the antenna terminals becomes large only when the antenna is able to collect more and more signal power from the space. Hence, we can understand that effective aperture is a parameter which is able to indicate the ability of an antenna to collect the signal that is coming from transmitting antenna. Effective aperture is related to physical aperture. The ratio effective aperture to physical aperture is called aperture efficiency. Effective aperture is also related to directivity, even though effective aperture belongs to one mode, receiving mode, whereas directivity belongs to another mode, that is transmitting mode. The relation is effective aperture is equal to directivity times lambda square over 4 pi. From this relation, one can see more the directivity, larger is the effective aperture. It implies when the antenna is good, working efficiently in transmitting mode, it also works efficiently, giving good performance when it is being used in receiving mode. Antennas, problems on antenna basics, part 1, series on antennas and wave propagation, lecture number 1.21. In the present session, we consider several problems and their solutions. These problems being set around field zones, field intensity, power density, radiation intensity pertaining to radiation emitted by antennas. To begin the session, we consider a problem, example 1. It is set on field zones of a transmitting antenna. For a dish antenna with an aperture radius of 5 meter, determine inner and outer radii of A, reactive near field region, B, radiative near field region, and C, Fraunhofer region. A transmitting antenna is surrounded by 3 regions. Innermost region is reactive near field region. Outermost one is Fraunhofer region. In between these two, radiative near field region exists. We are asked to inner and outer radii of these 3 regions. Solution. Aperture of dish antenna is its dia, and in the given case it is 10 meters. Radius is 5 meters. Naturally, dia becomes 10 meters. A part. Reactive near field region, it is the nearest region to the antenna. Inner radius is obviously 0. Outer radius can be determined using the relation r equal to 0.62 square root of d cube over lambda. Lambda is wavelength, it is not given. D is available, it is 10 meters. Substitution of 10 meters for D gives us our outer radius as 19.60 over square root of lambda. B, radiative near field region. It exists next to reactive near field region. Hence, its inner radius is outer radius of reactive near field region, which we have already calculated. It is equal to 19.60 over square root of lambda. Outer radius, it can be found using the relation r equal to 2 d square over lambda. D is 10. It gives outer radius as 200 over lambda. C, Fraunhofer region. It is outermost region surrounding the antenna, transmitting antenna. Its outer radius is infinity. Inner radius is outer radius of radiative near field region, which we have already calculated and found as 200 by lambda. Another problem, example 2. Determine the maximum distance between transmitting and receiving antennas when transmitting antenna is A, 5 meter long dipole antenna, and B, a dish antenna of radius 10 meters. Solution. The receiving antenna is always required to be placed in far field region, far field zone or Fraunhofer zone. Hence, a minimum distance between antennas is required to be maintained, which is equal to inner radius of far field zone. We consider a part now. Transmitting antenna is 5-meter long dipole antenna. In this case, longest dimension is 5 meters, and hence D is 5 meters. Hence R is the minimum distance that has to be maintained between transmitting antenna and receiving antenna. It is 2 d square over lambda. As D is 5 meters, R becomes 50 over lambda. B part. In this case, transmitting antenna is dish antenna. Radius is 10 meters. So largest dimension. Notice D in these formulas. Formulas we are using in this slide as well as those which were used in the previous problem, example 1 also. D stands for largest dimension of the transmitting antenna. In the case of dish antenna, largest dimension is its diameter, twice the radius. It is 20 meters in this case. So R, minimum distance between antennas, turns out to be 220 square over lambda equal to 800 over lambda. Now we consider another problem, example 3. The power density is equal to 200 microwatts per meter square due to a point source in free space at a distance of 20 kilometers. What is power density at a distance of 25 kilometers from this source? This is the problem. A source is there in free space. It is giving a power density 200 microwatts per meter square at a distance of 20 kilometers, and we are asked to find power density at a distance of 25 kilometers. Solution. Power density is inversely proportional to distance square. Power density decreases with the distance. The relation is inverse distance square 1. PD, power density, is inversely proportional to R square. Therefore, PD2 by PD1. PD2 is power density at a distance R2. PD1 is power density at a distance R1. This ratio PD to PD1 becomes equal to ratio R1 square to R2 square. Given PD1 is 200 microwatts per meter square, R1 is 20 kilometers, R2 is 25 kilometers. Substitution gives us PD2 as 128 microwatts per meter square. Notice as distance is increased from 20 to 25, power density got reduced from 200 microwatts per meter square to 128 microwatts per meter square. Another problem, example 4. Find the power density at a distance of A. 500 meters from a 500 watt source. B. 2 kilometers from a 250 kilowatt source. C. 36,000 kilometers from a 3 kilowatt source. Here consider the source is isotropic. Solution. A source is there. It is said the source is isotropic. Isotropic means it is radiating equally well in all directions. And we are asked to find power density at different distances when it is transmitting different amounts of powers. If power radiated, total power radiated by the source is PT, then power density at a distance R, it is PT by 4 pi R square. This is PD. This relation we are going to use in solving this problem. Solution part A. Here R is 500 meters, PT is 500 watts. Power density PT 500 by 4 pi, R is 500. Substitution gives us power density as 1.6 into 10 power minus 4 watts per meter square. B. We follow the procedure, same procedure followed in part A. In B, distance is 2000 meters, transmitted power is, total transmitted or radiated power is 250 watts. Substitution gives power density as 4.97 into 10 power minus 3 watts per meter square. In C, distance is 36,000 kilometers. Total radiated power is 3 kilowatts. It gives power density as 1.052 into 10 power minus 13 watts per meter square. Another problem, example 5. An antenna with a directivity of 32 dBi taking an input power of 2 kilowatts is giving a power density equal to 2 milliwatts per meter square at a distance of 10 kilometers in the direction of maximum radiation. Find its radiation efficiency. Directivity is given 32 dB. It is taking an input power 2 kilowatts. It is giving a power density equal to 2 milliwatts per meter square at a distance of 10 kilometers. This is the data. Now we proceed to solve the problem. Solution. Directivity is 4 pi times the ratio of maximum radiation intensity to total radiated power. So the total radiated power is 4 pi times the ratio of maximum radiation intensity to directivity. Radiation intensity is product of power density with distance square. Thus, maximum radiation intensity from the given values can be found as 2 into 10 power minus 3. This is 2 milliwatts per meter square. This is power density into 10 power 8. This is distance square. It gives 2 into 10 power 5 watts per steradian as maximum radiation intensity. Given directivity is 32. This is in dB. We can convert it into absolute units. It is 1584.9 in absolute units. 1584.9. Total radiated power then becomes, this is total radiated power, 4 pi into 2 into 10 power 5. This is maximum radiation intensity divided by directivity, 1584.9. Total radiated power now is 1.586 into 10 power 3 watts. Now radiation efficiency. It can be obtained by considering ratio of radiated power to input power. Input power is 2 kilowatts. Total radiated power, it has been found. We use that quantity here, 1.586 into 10 power 3. Radiation efficiency now turns out to be 79.3%. Another problem, example 6. A hypothetical isotropic antenna is radiating in free space. At a distance of 100 meters from the antenna, total electric field is measured to be 5 volts per meter. Find A, power density, and B, power radiated. We are given field intensity. We are asked power density. Power density is power flowing per unit cross-sectional area. It can be obtained from a Poynting vector E cross H. This is power density, yes. In case of radiation, which is a TEM wave, uniform plane wave, E and H are normal to each other. and E to H ratio is eta. It makes E cross H as E square by eta. So power density is E square by eta. Eta is 120 pi in case of free space, 377 ohms. Notice sometimes we are using PD to denote power density. PD, yes, both denote same thing, power density. Solution. The radiation field intensity E is related to power density S through S equal to E square by 120 pi watts per meter square. Given that radiation field intensity E is equal to 5 volts per meter, A, power density now becomes 25 over 120 pi. It turns out to be 0.0663 watts per meter square. B part. The total power radiated is equal to power crossing a spherical surface of a radius 100 meters. So it is product of spherical surface area with power density. So second part or B part is about finding total power radiated. Here is source, it is radiating, it is isotropic. So radiating equally well in all directions in the same manner in any direction. If we want total power radiated, one way is imagine a spherical surface around the radiator. Let us say having a radius of R. As the source is isotropic, power density, it remains the same at all points over this spherical surface, or power crossing per unit area of this surface, spherical surface, remains the same. It doesn't vary. Hence total power crossing the surface, which is equal to total power radiated by the source, becomes equal to power density multiplied by surface area of this imaginary spherical surface. So PT, total radiated power, is power density multiplied by area. Power density is already calculated, available. It is 0.0663. Area is 4 pi r square, 4 pi into 10 square. It turns out to be 8.284 kilowatts. Another problem, example 7. Calculate the maximum possible power density at a distance of 5 km from a transmitting antenna of directivity 3.5 dB and at an efficiency of 80% when its input power is 10 kilowatt. Solution. Here it requires to be reminded of the fact that power input to the radiator, a major part of it gets radiated into space. A small part of it, however, gets dissipated, goes into losses. Power radiated to power input to the radiator is efficiency. With this understanding, let us proceed to solve the problem. Given that efficiency is 80%, input power is 10 kilowatt P in. So the total radiated power becomes efficiency multiplied by P in. In the present case, it turns out to be 8 into 10 power 3 watts, 8 kilowatts. The directivity of antenna is given as 3.5 dB. In absolute units, it becomes 2.238. Then the maximum possible radiation intensity is directivity multiplied by total radiated power divided by 4 pi. This is from definition of directivity. Hence, maximum radiation intensity, it is 2.238 into 8 into 10 power 3 over 4 pi. Its value turns out to be 1.432 into 10 power 3 watts per steradian. The maximum possible power density is maximum possible radiation intensity divided by distance square. Power density, distance square. This product is radiation intensity. Therefore, maximum power density is maximum radiation intensity over distance square. It turns out to be 57.28 micro watts per meter square in the present case. Another problem, example 8. Maximum radiation intensity of a 90% efficient antenna is 200 milliwatts per steradian. Find the directivity and gain as dimensionless as well as in dB. When A part. Input power is 125.66 milliwatts. B. Radiated power is 125.66 milliwatts. Notice A is when input power is 125.66 milliwatts. B is when radiated power is 125.66 milliwatts. Solution. A. When input power is 125.66 milliwatts. Given that efficiency of the antenna is 90%, so radiated power becomes, total radiated power becomes efficiency multiplied by input power, 0.9 into 125.66. Here it turns out to be 113.094 milliwatts. The dissipated or loss power then is P loss. It is input power minus radiated power. In the present case, it is equal to 12.566 milliwatts. Given that maximum radiation intensity is 200 milliwatts per steradian, here is given. The directivity is 4 pi times the ratio of maximum radiation intensity to total radiated power. So D is 4 pi into 200. This is maximum radiation intensity over total radiated power, which is 113.094. It gives directivity as 22.23. In dB, it turns out to be 13.47. We are asked to find directivity and we obtained directivity here. Now gain. Gain is 4 pi times ratio of maximum radiation intensity to total input power. So G is 4 pi into 200 over 125.66. It turns out to be 19.89 equal to 12.98 in dB. Here we are asked to determine directivity and gain we have already obtained. This part, dissipated or loss power, it is not asked in the problem, but still we have done it. We have found the power dissipated as losses or in losses. Now the second part, B part, when the radiated power is 125.66 milliwatts, the efficiency of antenna is 90%. Input power now becomes PT over eta. 125.66 over 0.9, input power becomes 139.62 milliwatts. Given that maximum radiation intensity is 200 milliwatts per steradian, directivity is 4 pi times the ratio of maximum radiation intensity to total radiated power. Umax is available, total radiated power is available. In fact, it is given. So directivity after substitution can be found as 19.89. In dB, it becomes 12.98. So directivity is obtained. The gain is 4 pi times the ratio of maximum radiation intensity to total input power. Umax is available. Pi we have already computed. input power. So gain can be obtained. In the present case, it is 17.90. In dB, it becomes 12.53. Another problem, example 9. If the input power to the antenna is 1.5 kilowatt and the radiation efficiency is 95%, find its radiated and dissipated powers. Solution. The input power to a transmitting antenna gets out by two different paths. One is by radiation, another is by dissipation. Radiation is a useful way, dissipation is useless way, wastage way. By definition, radiation efficiency is ratio of radiated power to input power to the antenna. So the radiated power is input power multiplied by radiation efficiency. Given that input power to the antenna is 1.5 kilowatt, radiation efficiency is 95%. Therefore, radiated power becomes efficiency 0.95 multiplied by input power 1.5 kilowatts. So total radiated power becomes 1.425 kilowatts. The dissipated power then is total input power minus radiated power. In the present case, it turns out to be 0.075 kilowatts. With this, we come to the end of the present session. To recap, in this session, we considered and solved several problems which are set around field zones, field intensity, field density, radiation intensity, directivity, gain, etc. of antennas. Hope this session is useful to you. We meet again in part 2 of problems on antenna basics soon.